Guys started. It's a little bit past time, and of course then we've got a lot to do. As you know, this class can be pretty demanding in terms of academics here. Let me do a little housekeeping here as we get started. I'll start with this. I'm going to kind of twist these again and say, all right, here is lab number 2. Scan through it, grab yours, or I know you guys turn them in as a group, so whomever wants it here. And then number 1 is right there. So there's your first 2 labs. And as far as homework to go back, I have only this first one here. Here is chapter 23. Okay? And so obviously you just turned in 24, or it looks like there's a couple of 24s here, and you're getting ready here to do 25. So my hope here today is to do more examples from chapter 25. I'll do that in a second, and after I kind of review here a little bit and talk more about 25. If things go well, and then depending on how the problems go, how quickly they go, we'll jump into 26. But that then reminds me that your first test, if you believe it or not, is coming up. Where did all the time go here? But your first test is chapters 23, 24, 25, and now what we're about to get into is 26. I have some good news for you in terms of the rigor of the material. These first 3 chapters I think were pretty challenging. The next 3 are, well, easy would be the wrong word, so maybe I should say easier than the first 3 that we did. But if I was kind of breaking down this semester, I kind of look at it, these first 3 are really hard ones, and we jumped right in the middle of them to get started. And then these next 3 are a little more straightforward. We don't really learn any new physics. We start to learn the applications of it. We go from the science over to the engineering, if you will. And so they tend to be easier chapters as we get more into the engineering and away from the sciences. And you'll see that here, although only one of those is on the test that's coming up here. So you have 3 hard chapters and then one fairly straightforward, not easy, but easier chapter here on capacitors. So that's where we're headed. Now, if you've looked at the syllabus, our test is scheduled for next Thursday. We're a little behind on it, so I have a question for you. And I think you know what I'm going to ask here. And it kind of depends really on where your math tests are. And they're next week? All right. Okay, so maybe for a double reason, I'm thinking of bumping it from next Thursday to next Tuesday. Not a week from today, that'd be 2 weeks from today. No? Why not?
I said yes.
All right, so let me put kind of a makeshift calendar on the board here. If this is Tuesday and then Thursday, today's what, the 18th? Okay, so here's the 18th. If I add 2, that's 20. If I add 7, that's 27. If I add 7, that's 25. If I add 7, that's what, 32? I guess that's not going to happen. We're in September, so 30 days in September, so it must be 2nd. Okay. All right, so, and I better double check this because I don't want to get the wrong information, but I'm pretty sure your test is scheduled for the 27th. Give it a chance to do one more chapter, or the rest of this one, and one more. And we really could squeeze it in, but that's kind of my concern, is kind of squeezing it in there. Yeah, 27th. So because of that, I'm thinking the 2nd makes a whole lot more sense. The bad news in that, though, is that the 27th would be a day where we kind of get started in the next material. In other words, I probably would start some material here, even though it's not going to be on the test. So that hopefully is, you know. But I do think you need some more digestion time. Anyway, like I said, also depends where your math is. But a lot of you are telling me that there's math tests this week too. So, like I said, all the more reason why the 2nd would make more sense. All right, so I will ask it maybe in reverse order, starting with the 2nd. And oh, by the way, the reason why I'm bringing this up now is because Don's going to do the review, as you know, and the question is, do you do it this weekend coming up if we have it on the 27th, or do we go to the next weekend if we have it on the 2nd? So it's important we kind of make a decision here today, not wait till tomorrow there. All right, so with all that said, how many of you would like to postpone it? 1, 2, Well, perhaps so. So, why that funny look on your face?
I had 2 tests for next week, so I'm going to be busy the entire following weekend because I thought I wouldn't have anything to do.
Which weekend?
The 28th, 29th, 30th. So, it would stay.
Yeah. All right, but for a lot of reasons, I think the second is better here. So, all right, so let's we'll go to the second. Don will do a review the weekend before the second, and that gives us then still some time here before the test. So we'll finish up this 24 today and get started into finish 25. We'll get started with 26. Maybe even touch on 27 before the exam. We'll see where it goes, but we'll have the exam on the 2nd. Good. All right, so that's our new game plan. So with all that said, let me grab a pen here and let me kind of recap what this chapter was about. I hope you got the following out of the lecture. I'll start with that big diagram. I think the diagram illustrates it really well here. If I have, say, the position of a particle, and in this case they're usually charged particles, the velocity, the acceleration, I can get that from the net force, which I can get the net force from the sum of the electric field or the flux, depending on which approach you want to take. And so, as I was saying here, this is our first chapter, 23. It's Coulomb's law. We learn the electric field from a point. You add up a bunch of points. That will give you the total electric field. Total electric field gives you the total force. Force gives you acceleration, velocity, and position. Fair enough. Then, in the second chapter, chapter 24, as you recall, we did Gauss's law. And Gauss's law gave us another way to find the electric field, which that is the force, blah, 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 blah. This chapter, then, we went into the approach of energy. And so I started the lecture last time with saying, hey, let's remind you of this whole idea of conservation of energy. If you could look at a potential energy, and so I introduced you to an electric potential energy with the analogy of gravitational potential energy. But if you did conservation of energy, you could find the velocity, and we did a number of problems like that. However, we said one thing about, or maybe I should even say more complicated than gravitational fields, is when you have a charge there and or I should say you have a field there and you put a charge there, you can't really say what direction the force is until you also say what kind of charge that field, positive or negative. And that's why it was always better to deal with the fields than it was to the forces. And so we always dealt with the field because that was well defined regardless of what was the secondary charge that you placed there. If you didn't place one there at all, perhaps, you still had a field. So we did the same thing with potential. And so we said potential will lead to potential energy, and then potential energy will lead to velocity. And then likewise, then we learned that taking the derivative of the potential can lead you over to the electric field, just like taking the derivative of the potential function led to a force. And so we left with this idea that if you know how to find the potential, or you can take any shape and chop it up into little points, add up those little points, and get the total potential. And we did that for a ring, and that's where we left off. We said, let's look at a ring, and we did. And then from that, I took the advantage of the ring and took its derivative in order to find the electric field. I also then did a conservation of energy to find the speed. And I think we had like a positive charged ring and an electron coming in. I think that was the charges we had. But now, let's extend on that. In fact, just kind of as a review, I'll go back to the ring for a moment. Let me call this picture up here. Here is what we had done in terms of a ring. So I'll go back to the ring. think it's warming up. I am bothered by the fact the light is flashing over here. Oh, no, it stopped flashing. I guess that's good. All right. Maybe just had to warm up there. But if you guys recall, let's do this. Let's ask this question. Could you find the potential at some point x from a ring that has radius a? Is that what they used again? Yeah. And can you find the potential at that point P? And here was the idea, that the total potential would be the summation of the potential from a little chunk of charge. Okay? And so let's go ahead and add it up here. And so looking at point P, scanning back to what they have covered in the, colored in gray, a little charge of dq would be up there. The first thing is to say is, well, the potential from that little gray chunk would be how much charge dq is on that chunk, and then divided by the distance away, and then don't forget Coulomb's constant, which I like to write with the permittivity of free space. So there is the potential, and now you just have to add it up around the ring. And looking at the geometry, we said, well, Coulomb's constant, we can just pull it out. R, well, R is the distance away, and if you use Pythagorean's theorem, you can see that it's a squared plus x squared is the square root. And so that is the distance away. More than that, for the ring, it's kind of nice because for the ring, all the charge is an equal distance away from the point P, so I can pull that out of the integral. Now when it's all said and done, the only thing I'm doing then is really doing an integral of the little gray chunks all the way around, which they call capital Q. And so we end up with this equation for the potential from a ring. And then if you recall in the last lecture, we used that potential to then find the potential energy of another charge, which then found the velocity and then took its derivative to find the electric field. Now let me not do that again, but let me illustrate it by taking the next step. Now that we know the potential at point P from a ring, could we ask this next question, which is, what is the potential and hence the electric field from a disk? All right, well, you've seen us do this many times here, I think. And so let's keep working on it, because I know these problems aren't so easy, but again, here's the mental picture. We're going to add a bunch of rings. So I'm going to start here with this ring, which they've got a little shaded a little darker here, and say, all right, how do I get the potential at some point P from the center of that disk along the axis of symmetry? Okay. I've got to add a bunch of rings. So I'll put here disk. Potential of a disk is a sum of the potential of a bunch of rings. And now let's add it together. And so, as I said, this was that first step. Add a bunch of rings. Here's the potential from a ring. Yeah. Oh, well, they're taking the change in potential. Well, what is 34 asking for? They're not, I mean, are they asking for something like the speed? Okay, so there it is. The question is, what is the potential difference? All right, so let me take your question. You said this is number 34? All right. So they're asking for the potential difference. That is the change in potential when you go from, and read it again, what? From the center? Point, okay, so here's point P, and then here is center. Well, we're comparing, I guess, the potential from a point charge And the point charge was defined, I guess, as potential equaling to 0 out at infinity. So this is, if you will, the potential equation where you grab the potential where the potential starts out at 0 out infinity. Now, I don't really have a charge here, but let's say I had a charge here. Then it would take energy to bring it in, bring it in, bring it in, and bring it into here. That's what this is doing. This is saying how much potential does it take to get to this point. Starting out at infinity, how much does it take to get here? The question you're asking is very different. The question you're asking is what's the potential from going from here to here? So you're already here, and you're going to here. Or maybe it's the other way around. You're already here, center, so that's your initial potential. And you're going out to here, that's your final potential. So what's the change in potential? If it helps, I'll go back to gravitational potential energy. I could say this is the surface of the Earth. I could say this is the location where you might say MGY has 0 potential, but you have a giant building and your box is already on the 4th floor. How much energy does it take to get to the 5th floor? So your interest is the change in potential energy, not its true potential. So you would say it's 5 meters. So this would be 25 meters, and then the 4th floor would be mg at 20 meters, right? And the difference then between them would be mg 5 meters, and I'd subtract this potential from that potential in order to find the change. And that's what they're asking here. They're not asking you to find the equation for the potential, but the difference between them. So using the potential at point P, I would have Q 4 pi epsilon naught square root of x squared plus a squared there. And then I would subtract what is the potential where it started with. So 5th floor, 4th floor. And then it starts at a position of x equals 0. So that's the change in potential from here to here. This is the equation for the potential referenced from 0 at infinity. That helps. So yeah, so be careful on reading what they're asking for, the difference between two spots or the equation for the potential as referenced from our point chart. Two different equations, obviously closely connected in the same way these are closely connected. This is our reference point 0. Our equation is mgy. But if you want to know the difference between delta and y, yeah. So this is really what you might call a change in potential, where I've got the potential at point P compared to the potential at infinity. Potential at infinity based on all right, so back to this disk then. I just thought it would be a nice integral to do yet again, since you've done a lot of them, or you're developing that skill now. But let's add up a bunch of rings. But the concept is this, that you get the disk from adding up the rings. So you got to jump over here to this equation for the equation for a ring. So 1 over 4 pi epsilon naught q, and then the square root of x squared plus a squared then is the, and I should be a little more careful here, but this is the distance. What is small, if you will? What is going to 0 if I replace this with, the sum of 1 over 4 pi epsilon naught q on the ring over an x squared plus an a squared square root? What am I taking the limit going to 0 to make this mathematically make any sense? What about the ring? The radius of the ring? The charge on the ring? The distance from the ring? What is going to 0? And I think this, like I said, is the harder part of these problems. Doing the problem in the sense of actually doing the integral, doing the math, usually isn't that hard step. That hard step is looking at that integral. And I heard a couple of you say it right here. As you are making this ring thinner and thinner and thinner, what are you making go to 0? Okay, the charge on the ring. Or some of you are saying the area of the ring. I would agree with both of those, although area is not in this equation. So I am not going to put area of the ring, but charge is there, right? And notice I am not putting the radius of the ring going to 0. When this gets thinner and thinner and thinner, the radius is still, they have it listed as little r. Right? That doesn't go to 0. And as this ring gets thinner and thinner and thinner, the distance, the x, doesn't go to 0. And so knowing what goes to 0 is an important step here. So in this case, I'll even put the word ring underneath it. Say, what is my little integrand? I got to know. That's where I get started. Is this a d? And so that's the crucial step here at the beginning. And as a lot of you already said, well, wait a minute. Isn't that the same as the area is going to 0? Well, they both go to 0. Little equation, although that's where I probably want to do my switch now. I want to switch it from a little dq to, say, a little dA here for the area. And so how is, say, a little area, dA, related to the little charge on the ring? And that's really kind of that next question. How can I take from the development of the equation to something that I can actually begin to do, something that instead of as a dq is a d something else. And I'll change it to dA, but even that's not going to be enough. But I think, yeah, good, some of you are saying it, and you can see it right here. What's getting smaller is there is a connection to dA. Your author probably too. I have a hard time using a capital A for a little area, but I know that we use capital A for area and we use the little a for acceleration. So I should stick by that notation. It's hard for me to call it a capital letter. That's why I changed it here from a little q into a big Q. It's just really hard for me to call a little something with a capital letter. I don't know why that is. But nonetheless here, I'm going to put, here's the charge density on the ring. It would be sigma, and we'll say charge on the ring divided by the area of the ring. And so that would be my next step as I solve this problem. I would say, well, this is 1 over 4 pi epsilon naught. I still have this square root of x squared plus a squared. And now, in place of dq, I'm going to put a sigma dA. And so I've changed what hopefully is an obvious step here, dq, to another hopefully obvious step, dA. One that isn't going to help me quite yet because it's not like a dr or anything. And so that's where the next step comes into play. You got to look back at the picture, look at the geometry. How is the area of this ring? This colored ring here, this darker one, how would you get the area of that thing? Well, your author gives it away here. I like to imagine kind of cutting it and laying it out. If I laid it out, it would be a rectangle, right? Its length would be equal to its circumference. So there's its length, 2 pi r. And its thickness would be, your author has labeled it as a thickness of dr, calling the little r the distance you are moving out. And so there's the length of this ring. There's the thickness of the ring. Length times width is area. And so that's the mathematical connection between the A and the R. So this becomes 2 pi r dr. Right? And so we're back to the type of problems we were doing in 23, as I mentioned. To get the potential, you got to add up a bunch of things. Okay? Just to recap, we added up a bunch of point charges to get a ring. Now we're going to add up a bunch of rings to get a disk. Think we could do this for a cylinder? How are you going to get the potential from a cylinder? Add up a bunch of disks. All right, you got the idea here. So time probably won't allow us to do all these different geometric shapes, but you get the idea here. But again, this is where you want to start. Think of it as a sum of a bunch of rings. You got to look closely at what's going to 0. Change that into something else, which changes that into something else. But eventually I get to a dr. Because now I can say, here's what I'm going to do. Looking at that picture, adding up these bunch of rings now makes sense. Because I would start with little r equal to 0. That would represent a small ring. And as the r got bigger and bigger and bigger until eventually got to a capital R, I would get the entire ring. And so these 3 steps, or from here to here 1, here to here 2, and here to here 3, are what I call the crucial steps. Because the next step's going to be easy. It's just going to be an integral. I mean, and not to say integrals are so easy, but that's not what this class is about. And our integrals don't usually turn out to be too hard of integrals, but it's those 3 steps. Oh, and I'm not done here. I avoided the square root, and I need to put it back. I'm going to change it to a 1/2 so I can see the integral a little bit better, if that's okay. But the reason I avoided it is because I needed to get some thought here between what I did in this step. Now, what was the radius of the ring here? A, right? And for whatever reason, your author has changed his notation, and that can be a little confusing. Because what should I put in place of A? Little r. Do you see that, right? The little r is the radius of the ring. So want to make sure you caught that. I am going to put a little r squared in place of the A. And for whatever reason, when he does the ring, he calls the radius of the ring A. Probably because he doesn't want you to confuse it with this r, right? This is the distance away. This is not the radius of the ring. This is the distance the point is away from the charge. So that's why he does it there. Then, later on, in this step, he wants to change the notation from an A to an R, probably because you're more used to seeing an integral with dRs, and that's what we're adding up. We're adding up Rs, we're adding up radius of rings. So he switches back to the little r. So this is the little r, the radius of the ring. Okay. Now the x squared, I think he leaves the x the same, doesn't he? Yeah, so the x is still the distance from the center of the rings that we're adding up. So that doesn't change anything. So I'll leave that as an x squared there. Okay. And so now there's my integral. And then fortunately, as I said, it actually comes out to be a very easy and doable integral. I'll do a little cancellation here, I guess. This 2 pi with the 4 pi cancels off. So the 2 that's left over can be factored out. The epsilon naught can be factored out. The sigma can be factored out. And now we're left with an integral from 0 to capital R of little r over x squared plus r squared to the 1/2 dr. And at this one you can do change of variables if you like. Call this a u downstairs. Personally, I just kind of like to maybe play a little bit with it because I happen to know it's going to be really close to that. It might be a negative, there might be a factor of 2, but I can see right away that if I took the derivative of that, then 1/2, when I lowered its power, would become a negative 1/2, right? So it's going to be that. And then the inside piece, when I do the chain rule, the r squared becomes a 2r, and so there's the r. And the fact that I've got a 1/2 and a 2 there tells me they probably cancel off. So I'm going to guess that that's the answer. It's probably pretty close. Like I said, it might have a minus sign. It might have a factor of 2. Just to kind of double check, I'm going to just stand over here on the side and actually take its derivative and see where that gets me. If I take the derivative, I get the 1/2. I get then the x squared plus r squared to the negative 1/2. I then get a 2r. That cancels off, and I do end up with an rx squared plus r squared to the 1/2. So that is it. There is no extra 1/2 or negative anywhere in there. So to me, that's a way that I started to do these kind of integrals back in chapter 23, and a couple of you asked me to do, do a substitution. And that's fine if you want to do a substitution. I just think it's a lot of extra unnecessary steps when you can clearly see that this piece upstairs, the chain rule of the piece downstairs. Nothing's better when an integral works out like that. It's like, yes, this is not an integral by parts. This is not a real complicated one. This is just a matter of looking at the details. Well, then I can do this 0 to r, right? And so, let me erase my ring here and get the answer I'm after, which is, what is the potential at some point P, and I guess it would be then this charge density 2 epsilon naught. And if I put in my first term, it would be an R. Where'd it go? Oh, on the far side there. Okay. So this would be my x squared plus the r squared to the 1/2 power when I put in the r. And then minus, and if I put in a 0, it looks like I get just an x. And so there is my equation for the potential from this disk. Okay? And again, as measured from the point at infinity. So if the problem said, find the change in potential as we go from point P1 to point P2, I would have to get, okay, here's the potential at P1, here's at P2, subtract the 2 to get there. All right? Oh, it depends how they word it. Yeah. If they go from 1 to 2, I guess you want to go final minus initial. So you want to go 2 minus 1. Yeah. And if they move the other way, then, yeah. Oh, so maybe I should take one more step. Good point. This is the charge density. I probably should go one more step. It kind of depends what they give you in the problem. I just threw this one out there. I know it's an example for you, but rule of thumb, you guys asked about this before, but this far in your education, I think you know. The general idea is to leave the final answer in the symbols or the information they have given you. So if they said that the disk had a uniform charge density of sigma, leave it like that. But on the other hand, if they had said that the total disk has a charge of Q, we need to take another step. They didn't give me the sigma. I invented the sigma along the way to solve the problem. It was important, don't get me wrong. And so I needed to take this step. But you don't want to finish your answer with a sigma if they didn't give it in the problem. And I think in this one they don't give you the sigma. They just say uniform charge density, and they say the total charge is Q. So I think that's what you're asking. So yes, I probably should take another step here and say this charge density can now be written then as a Q over pi r squared 2 epsilon naught. And that way, I am putting the final answer in the symbols they have given me. And so I'll put the Q here, I'll put the 2, the pi, the epsilon, the r squared, and then I will put the x squared plus the r squared to the 1/2 minus the x. So that's a good point. It's probably a better way to finish this problem if, like I said, depends what they have given me in the problem. Yeah.
Is it supposed to be capital R in there, or what?
Oh, which step?
Just on that board.
Yeah, this should be capital R, because what I'm doing is this is an integral where little r goes from 0 to capital R. So I'll first put in the capital R here, and then minus putting in the 0. Okay. So there, like I said, is my equation for my potential. Now, I've erased it since I've been working on this, but why would I care about the potential? Well, one option is, what if I take the derivative? Wouldn't that get me the electric field? So let's go ahead and do that. We actually found the electric field from a disk back in chapter 23, if you recall. Let's see if we get the same thing. We should, right? And I think this is a little easier than what we did in chapter 23. That's kind of a judgment call, but at least now we have options of which way we can go. So while you're doing the test, I think one of the toughest decisions you've got to make when you start that problem and it says find the electric field, you have to go, ooh, which way do I want to find the electric field? Do I want to do it with Coulomb's law, where I add up the electric field from a bunch of point charges? Do I want to find it with Gauss's law, which is looking at the flux? Or do I want to find it this way, which would first really find the potential and then take the derivative of the potential? And so there's advantages and disadvantages of each of those. And I think you can kind of see that. Back in Coulomb's law, finding the electric field from the disk was a bit challenging because the electric field is a vector. So you've got to worry about its magnitude and its direction. On the other hand, finding the electric field from the potential can have its challenges because first you have to do an integral to add everything up and then take a derivative of that. So you're kind of asking me to do a lot, but I don't think derivatives are too challenging. And in this case, I would say this is probably a better way to find the electric field from a disk by adding up and getting the potential and then taking the derivatives. Because when I'm doing the integral here did not involve directions, where it would have, and it did need it for the electric field. Okay? But that's a tough call, one that you have to develop that skill. That's why you've got those long homework problems and you spend all your whole weekend with your buddies and doing homework, right? Because you got to kind of look at, what is the better approach here? And that's where this class begins, electric field. That's why we have 3 chapters here on discussing the electric field. All right, so finally I'll get where I'm after, which is, okay, what is the electric field along the x-axis here? Along that axis of symmetry for my disk. And that would be negative and depends how you want me to write it, derivative of the potential. And as I said last time, what we really mean is take the derivative of the potential, let x be your variable, but if there's a y in there or anything, treat that as a constant. Now, we don't have that issue here, so it's not really a difference there, but that's kind of what we were saying back when we said, hey, let's do some partial differentiation. All right, well, if I take the derivative, I get a negative, I get a q, I get a 2 pi epsilon naught, I get an r squared. Those are all constants. And then I've got the derivative of this crazy thing. So that is a 1/2. And then it would be, I guess, an x squared, r squared to the negative 1/2. And then it would be a 2x. So there's the derivative from the first term. And there's the derivative from the second term. I'll just rewrite these constants out here. And then I'll kind of simplify. I'll start with putting that negative with that negative and making a +1 there. So I'll put the 1 first because that's how we saw it back in chapter 23. We saw it as a 1 plus. So, I'm sorry, 1 minus. My bad. It's a +1 and then the minus here makes a minus. The 2's go away and you're left with an x in the top and you're left with an x squared plus an r squared to the 1/2 down in the bottom. Yay! There we go. Right? And so there is the electric field. And if I'm remembering right, that is the same thing we got way back in chapter 23 where we added up point charges and added up their electric field and came up with that whole idea of a ring. So,
How'd you get the
Right here? This one? You mean how did I go from here to here, or how did I go from here to here? See, from here to here, I'm taking the derivative. So the derivative of x is just 1. No. All right, well, that's kind of where I was hoping to leave off last Thursday. Let's open the book now. Let's look at some examples out of the book. I got a list here of ones I like to do out of the book so you can reference them, and usually the ones out of the book actually have concrete numbers where we can put in the numbers and find them. In fact, I think one of them I have listed in the book is the ring again, where we did last time, so maybe I'll just do it again to make it kind of sink in here, or maybe I'll say let's move forward. I don't know. I think I'll do it and just kind of do it quickly. Again, I don't think you can see this enough times. And it just takes time to soak in. That's why I was kind of hoping you guys weren't having math tests the first week in October, and just give it time to soak in here. And the more time, the better here. Well, the first on my list, I got number 55. Number 55 is kind of a little different than the ones I've been showing you so far, so I thought I would start there so we're not kind of doing the same thing again and again here. But let's read it here together here. 55 says this. It says, calculate the work that must be done to charge a spherical shell of radius r to a total charge of q. Now, they don't really say that this shell is a conductor, but I'm going to go ahead and make the assumption that they do mean a conductor. If they don't mean a conductor, they probably mean charge it uniformly. So when we bring in charge, we bring as much onto the top of the sphere and the bottom and the left, the right, the front, and the back here. So calculate the work that must be done to charge a spherical shell of radius r to a total charge of q. I mean, let's just talk about this for a second here. Here is this spherical charge, all right? And we're going to charge it up. Well, let's say we're bringing in positive charges here, all right? And so maybe I'll start way over here at infinity. So here's my positive charge. You might say this is a little bit of charge, dq. How much work is it going to require of me to put the first one on there, let's say? Well, yeah, anything stopping me from getting there? Anything helping me get there? No, if this ball was charged, would that change? Yeah, so I'd say the first one's real easy. The first one, as soon as you put a charge on there, now we have a different story about the second one. Is it going to take some work to get the second one on there? Yeah, because now this charge is opposing that charge, right? And so there's going to take some work. And then what about the third one? Even harder still. The fourth one, fifth one, the sixth one. How are we going to get the total amount of work? Are we going to add them all together? And are we going to break it down into little pieces? Isn't this going to turn into an integral? It's going to turn into an integral you've never seen before, but you could drive yourself. Whoa. Isn't that cool? All right. That's this idea here. So how much is it going to take? All right. Now, the reason I said I'll go ahead and pick a sphere that is a conductor is, what do you know if I put a little bit of charge on there? What have we learned from the past chapters? Yeah, it's going to spread out. And the concentration of that charge really is based upon the curvature. And a sphere has the same curvature. So doesn't it just have a nice uniform charge distribution? Which will also help me out, because we learned this before too. What is the electric field created from a shell of charge? It's the same as a point, right? So let me ask you this. Do you know the potential that's created from a spherical shell? We do. Isn't it the same as a point? I mean, maybe it's worth looking at again here. This is what we did in the last lecture. I'll put it over here on the side. We did this. We said, look, if you took a little point charge, that little point charge is going to create an electric field, E. The value of that equation is 1 over 4 pi epsilon naught times the charge Q that you place there divided by your distance away, squared. Right? That's the electric field. And the change in potential then would be an integral of this electric field over some distance, right? Wasn't this our fundamental definition then of the voltage change? And so if you recall, what we did is we said, well, let's start at our initial. Let's move to our final. And when we did that, we put in this, oh wait, must be a negative there. We put in the electric field. And the electric field was 1 over 4 pi epsilon naught. The charge is then AQ. The distance is R squared. We're moving dr. And when we did all that, we got 1 over 4 pi epsilon naught Q over R evaluated from some initial point to some final point. And so we finished it by saying this then would be the generalized equation for the potential from a point charge. It came from integrating the electric field. And so one of many reasons I grabbed this problem is I want you to see that we can do this problem. It's not going to be too hard of a problem, at least in terms of math. And there's not much to write on the board, but there's a lot of this going on in my head. Okay, wait a minute. What is the equation for the potential? And so I claim that without actually going and doing Gauss's law, because if I did do Gauss's law, wouldn't this give me the electric field on the outside? Didn't we already do that? And then if I integrated the electric field from a distance, wouldn't it be the same formula and hence the same equation for the potential? So I claim that outside of this ball, wherever you want to place yourself, and so we'll start with charges really far out as we bring them in. Maybe I'll just put the equation right here. But one of the first things in my logic here is that the equation for the potential created by that ball over here, a distance r, is this formula. Fair enough? And that's what you need to be convinced of first. That even though we haven't done a spherical shell in terms of potential, we have done it in terms of Gauss's law and realize that the electric field is the same and hence the potential is on the same, at least on the outside. But I'm only going to care about the outside because let me go back a chapter. Didn't we learn that the electric field on the outside was the same as a point charge, but on the inside there was something different going on? And there's no point on this one of talking about the inside here because we're not going to go on the inside here. We're just going to move the charge up to the ball and put it on the surface. If we were moving along in the inside, there might be more of a question on that. Okay? But again, if it's a conducting shell, what do we know about the electric field on the inside? Zero. So what would be the change in potential as you moved around on the inside? Zero, right? The integral says, hey, integrate 0. So there is no change in potential as you move around. So whatever potential you get on the surface then is going to continue all the way through. And here's my point then. Let's say we are doing this problem and we are coming with this little point charge Q and we bring it in. How much energy would it take to bring this little charge dq to bring it all the way to the ball, assuming the ball at this moment already had a charge Q on it? Okay? So, again, let me make this clear. You already told me the first charge is real easy to bring in. It doesn't take any work. I agree. But halfway along this process, that ball has a charge of Q, and I'm going to bring in a dq. How much energy would it take? All right, well, let's call this a little bit of energy. Didn't we learn that the energy is the charge you bring in times the potential, right? And so here's how I'm going to come up with my own equation. What I'm going to say here is somewhere halfway through this process, I would say that this ball has a charge Q on it. So the potential of this ball, then, as I bring it in from infinity here, is 1 over 4 pi epsilon naught. Okay? And then, see if I say this right to you, it would be the charge on the ball. Should I write it with just capital R? Or maybe I should write it as starting at infinity and going to capital R, where capital R is the radius of the ball. How about that? Wouldn't that be, and maybe I should have put change, wouldn't that be the change in potential? As I take this guy out here, which is really 0 potential, and I bring it in, and I bring it in, and I bring it in, oh, and then times that charge. And so the change in potential is that, times the charge I bring in is that. Fair enough? No. All right. I see a lot of blanks here. What am I missing? So the uppercase R is the radius of the ball. Yeah. So the change in potential would be, what is the final point you start at compared to the beginning point? Okay. So the final point is radius capital R. The beginning point is infinity. So the change in potential, as I move this little charge out from infinity onto the surface of the ball, is that. Fair enough? So that is our change in potential. That's what I meant with this notation. Final minus initial. Okay? And then I multiply it by how much charge I am bringing in. And so I'm talking about just bringing in a little piece. Okay? And so this would be just a little change in potential. Okay? Like I said, there's not too many math steps in this problem, but there is a lot of physics steps. That's why I thought it would be a good problem. Okay? I got to realize it's the same electric field. I got to realize it's the same potential. And then the energy to bring a little chunk in would be this, which is the change in potential times how much I'm bringing in. Okay? Now, the problem is more complicated than just how much does it take to bring in a little bit of charge. Isn't it how much to charge the whole ball up? So let's finish the problem. The problem then says, what is the total energy as you add it up? That is, you start with 0 and you go all the way to capital Q. Right? So we start with a little sphere that has no charge on it. Hence, the potential is 0. How much energy does it take in to bring a little bit of charge multiplied by 0? 0, right? But now, after you bring that first chunk of charge, the ball does have a charge, Q. And the next chunk is going to take a little more energy. And of course, now that little chunk has a bigger Q. You bring in a dQ, and it takes a little more. Now you got a bigger Q. You bring in another chunk. And every time you bring in a chunk, it's a little bit more. And so we've got an integral that looks something like this. 1 over 4 pi epsilon Q over R dQ added up from a little bit of charge to a full charge of capital Q. And when you do all that, you can see that, surprisingly, maybe, we end up with a very simple integral, one that you probably could do in your sleep now that you've done calculus a long time ago. What's the integral of Q dQ? Yeah. 1 over 4 pi epsilon over r. And then this would be q squared over 2 evaluated from 0 to capital Q. And so I get 1 over 4 pi epsilon. I get r. And then I get a capital Q squared over a 2. And so maybe the whole thing should look like this. Total charge squared, 8 pi epsilon naught over r. Right? And so there is the total change in energy to bring it in. Right? I see a lot of blank stares. All right. Too fast today? Too hard? Too confusing? So the question was this. The question says, 55, calculate the work that must be done to charge a spherical shell of radius capital R to a total charge of capital Q. Okay. And that's how I set it up here. I said, all right, let's ask this question. How much energy would it take to bring in just a little chunk of charge once the ball is already charged at Q? And so I took the potential and times the charge. And now I have to add it up because I have to bring in a first chunk and a second chunk and a third chunk and a fourth chunk. I have to keep adding it up until I get to capital Q. And again, I don't think the integral is going to throw anybody off. What I think is coming up with the integral is going to throw people off. And so there's the total energy it brings to charge up the ball. Okay? And you can kind of see that in terms of a graph. If I was then making a plot of how much potential energy did it take for a charge Q, you can see that it's quadratic, right? Total charge Q. And so if you're going to charge the ball just a little bit, it really doesn't take much energy. Which again kind of makes sense, right? It doesn't take much energy to put the first charge. In fact, it takes no energy to put the first charge on there. Then it takes a little more and a little bit more. And then if that ball starts to get a lot of charge on it, boy, it's really going to take a lot of energy to charge the ball once you've already got a lot of charge on there. Because to put one more charge on a ball that's already charged is a lot of energy.
Can you say again, like, how you got that first equation with du? Like,
You good with this one?
sort of.
All right. Well, then I'll backtrack on this one. This is what this chapter is all about. What's the definition of potential? It's how much energy do you get for one chunk of charge. Okay? So, if there is a small change in potential, there'll be a small change in energy. So take a little chunk of charge, multiply it by the change in energy, and you're going to get a du. All right? And so that's what I'm looking at. I'm going to look at, okay, what is the change in potential when I go from way over here, infinity, to the surface of the ball? Well, the equation for potential is going to be the same for a point charge, so there it is. There's the potential when you're at radius r. There is the potential when you're at radius infinity. So that would be the change in potential as you go from one step to another. So that's this first term. How much charge am I thinking about bringing in? Well, let's just do it little by little. So I'm going to call it a little dq. So I'll take this and bring in a little dq. That's the first step. And then what I call the physics step. And now we've got to do some integration. And that's where you go with that. All right, question. Yeah.
Should that integral from 0 to r be sort of
Yes, thank you. Yes. 0 to q. Right. I'm adding up chunks of charge. Putting on the first one, second one, third one. All right, well, there's a good, I told you it was a different one. Shall we try the 59? 59 is, this is the one that we really kind of already did. So let me do it again here. They've got the ring again. Maybe I'll leave that down. Doesn't give me much board space, but there's a couple of nice pictures on the next one here. You can see. But this is the one I did on Thursday. It's probably worth doing again. It does have this equation in it, so I think it's worth repeating here. Okay. Number 59 says this. It says the x-axis is the symmetric axis of a stationary uniform charged ring of radius capital R and charge capital Q. All right, so why don't I just draw that first? Here is kind of a ring. Here is the x-axis. They say that the x-axis is the symmetric axis of a ring that has radius R and charge Q. Okay, so we're back to our ring. I'll read it again. The x-axis is the symmetric axis of a stationary, uniform, charged ring of radius capital R and of charge capital Q. A particle of charge capital Q and of mass capital M is located initially at the center of the ring. All right, so at the center of the ring, there is a little particle of mass capital M. It also has charge of capital Q, so it has the same charge. Without me reading further, what do you think is going to happen? They repel each other, right? Now I suppose right in the center there's that delicate balance of trying to balance a pin on its cap. And if you just barely get off, it goes shooting one way or the other, right? And so that's what's going to happen here. We've got what we call an unstable equilibrium here right at the center. So any slight vibrations, it gets off center and then the force keeps pushing it away. So an unstable equilibrium. So there's our little chunk of charge. All right, so far so good. Got a picture of it? I'll keep reading. When it is displaced slightly, okay, so that's like me tapping that pin right there. The particle accelerates along the x-axis out to infinity. What is the equation for the velocity as it gets far, far, far from the ring? Okay, so what's the velocity? How are we going to find that? Well, again, that is the point of this chapter. Couldn't we do from potential? What could we get from potential? Either A, use conservation of energy to get speed, or B, take the derivative to get electric field. And you've seen both of those. This one is obviously asking about conservation of energy. So what I would do is start off with the first question of what is the potential then from a ring? Well, should we run through it real quick? Are you sum of a bunch of chunks? A chunk is 1 over 4 pi epsilon times that little chunk dq, distance away. If you're some distance x and you've got a radius of r squared, there is that distance. You can factor out the 1 over 4 pi epsilon. You can factor out the x squared, the r squared, and the 1/2. Then you got an integral of dq. That is just capital Q. So our equation for the potential from a ring, which we did, 20 minutes ago or something, is q over an x squared plus an r squared to the 1/2. There it is, right? And of course, you're going to have to make this decision for the test. Do you try to memorize that equation, or are you just kind of work it out from the beginning? Personally, I just kind of work it out from the beginning. If I have a whole list of equations to memorize, it makes me feel like I'm just plugging and chugging and I'm going to foul something up here along the way. So let's derive it as you go along there. So there's the equation for the ring. I hope I got the same thing I got 20 minutes ago. That looks like the same thing, right? Okay, so now that I know the potential, I can invoke this whole idea of the definition of potential. The change in potential is related to the change in potential energy. So, as I say, what is the energy? It would be the charge that you place there times the potential. Okay, now in this case, the charge I'm going to actually place is a Q. Whether I place it here to begin with or later on it's out there, but the charge I place there is a Q. I place it in a potential that is given by this equation. Another Q over a 4 pi epsilon naught and x squared plus an r squared to the 1/2. So this then is the equation for the potential energy of that movable point charge, capital Q, set along the axis of symmetry of a ring of radius r and of charge q. That is the potential energy. So as I invoke my conservation of energy, I would say initial energy is equal to final energy. I'll start at the beginning, that is this little chunk of charge, capital Q, is then placed right at the center of the ring. So the first step is to say, well, how much kinetic energy does it have? 0, right? So I'm going to put in a 0, my kinetic energy. They say just place it there. How much electrical energy, electric potential energy does it have? Well, that's why I worked out this equation, which came from this equation, which came from the integral of the potential from a point charge. So again, see that strategy? I know the equation for a point charge. Integrate it to get the potential from a ring. Once you have the equation for a ring or whatever shape it is, then multiply that by the charge you place there, and that's the equation for the energy there. So I am going to then say that this is a Q squared over a 4 pi epsilon naught, and I am placing the charge Q at position 0, right? I place it right at the center, x equal to 0. So that is how much potential energy this thing starts with. Then, what happens to it? Well, as we said, it's slightly disturbed. It gets bumped a little bit, goes racing off, keeps going out to infinity. By the time it gets really far away, it's going pretty fast. It has a kinetic energy equal to that. 1/2 mv squared. That's its kinetic energy. How much potential energy does it have at that point? Right, x goes to infinity, so it goes to a 0. And now I can simplify things a little bit. I'll put a 2 over there, I'll bring the m over there, and then take the square root. So q squared over a 2 pi epsilon naught, an r, a capital M, raised to the 1/2 power, and there's my velocity. So there's the equation of the velocity, and I hope it agrees with what your author has here, yep, in the problem, where he says work out the problem and find out what the speed will be when it's really, really far away. Okay? What if there were 2 rings? What would you do there? Yeah, superpositioning, right? Somebody said, oh, well, look, here's one ring. If there was, say, a second ring, maybe a little further back, which might actually be enough to give it that disturbance, then my potential would be the potential from one ring plus the potential from the other, right? And so I would just go back to this step right here and say the total potential is 2 rings. So I'd have one equation and another equation. Now that other equation would be marked from a different distance. So assuming that the other ring still had a charge q and still had a radius of capital R, but was placed a distance d further away, maybe I would have something like that, right? Where my second ring is now a distance d away. So the potential I get from that ring would be based upon how far you are from the center of that ring, which is your x-axis plus a little extra distance, d. And that would be my potential. And I would put that then here to get the potential energy. And then I would do the potential energy to get the velocity. What about a third ring, fourth ring? Right? Infinite number of rings. All right, well, maybe that's a little extreme there. Okay? But just trying to lay that out there. But that now you have the skills, at least in theory, of could you do any shape? A bunch of rings making a disc, a bunch of discs making a cylinder, right? A bunch of points making a line, a bunch of lines making a rectangle, a bunch of rectangles making a solid, rectangular solid, right? And so that's the idea of calculating the potential. Well, like I said, that's 59 there. How about we try 58, 58. 58's got a nice picture to it. And again, it kind of illustrates this same point of, where did 58 go? 58, there it goes. I saw it somewhere right there. Here's the picture the author gives you. You got 4 little charges there. Here's what the problem says in 48. It says 4 charged spheres, each with a mass little m, are connected by 4 non-conducting strings to form a square of side A as shown in the figure. All right? So there's the picture, right? 4 little spheres, 1, 2, 3, 4, separated by A with these strings. Now, it's important to realize the strings, they say, were non-conducting strings. So if we put a charge on one, it can't flow to the other one. Okay? The assembly is placed on a horizontal, non-conducting, frictionless surface. So imagine that laying on a table. Okay? So we got a little square laying on the table. Spheres 1 and 2 each have a charge Q. So 1 and 2 are colored because they got a charge Q on them. But 3 and 4 are uncharged. Okay, so there's no charge on 3 and 4, but there is on 1 and 2. And the charge is Q, so they have the same charge. Find the maximum speed of sphere numbers 3 and 4 after the string connecting 1 and 2 is cut. Should I read the question again? What are we after? Find the maximum speed of ball 3 and 4 once the string between 1 and 2 is cut. All right. So think about that. What's going to happen here? I mean, what do you think might happen once I cut that string? Yeah, so there's the physics part of it. We got a lot of math to do still, but the physics part, and a lot more physics than just that. But the physics part is 1 and 2 are going to do what? Yeah, they're going to push apart, right? They're like charges. All right, now carry that through. Once they start pushing apart, do they fly out to infinity? No, why not? They got still strings holding them together. All right. So again, what is going to happen, you think? So they won't do this, right? But they'll do what? Will they rotate down like this? Now let's keep going. Is that all that will happen? What else will happen? Won't they go past that? And then what's going to happen here? Yeah, they're going to come together and slow down, right? Eventually stop. So it'll be a square again. Until the one will be kind of doing this. Right? Do you see that? And there's still some more physics I'm going to ask you to see. But I just want to start there. Because again, here it is. It says find the maximum speed. And so you've got to have the physics behind it. As you think mentally of this thing kind of flapping like this, where would it have its maximum speed? Yeah, a straight line there, I heard somebody say. So let me draw that picture over here. Your author has the starting position But I claim that ball 3 and ball 4 and now 1 over here and 2 over here is the diagram when they are at their maximum speed. And I agree. Why did you say that when they were in straight line? Yeah, I would answer in terms of energy. Somebody said in terms of oscillations, and that's fine too. But I would argue it in terms of energy. When is it going to have its most kinetic energy? Well, I should say, when does it have its most speed? When it has its most kinetic energy. When does it have its most kinetic energy? When it's least potential energy. And these are like the problems we did in Physics 121 with the roller coaster, right? The roller coaster goes up and down, and the problem said, find the maximum speed of the roller coaster. And the clue to you was to realize maximum speed means maximum kinetic energy. Maximum kinetic energy meant minimum potential energy. So you looked at this roller coaster and you said, where was the roller coaster the lowest? Because that's where it had the least potential energy, right? And so in that sense, I think it's the same problem. Okay? And so now we got to find that configuration. And you're right, that is the configuration. And so now we have to apply conservation of energy to find out then what is the speed. And so let me do that. I am going to say initial energy is equal to final energy. Let's start with initial. In terms of electric potential and electric potential energy, I'm hoping this one's not too hard. It's just two charges, 2-point charges. Could you tell me the potential energy from that? Sure. Maybe I'll put a little diagram back here. Here's 1 and 2. 3 and 4 are kind of irrelevant when we talk about the potential energy. But wouldn't the potential energy, U, be equal to the potential that is created by, say, charge number 1, and then you place charge number 2 in its presence, right? And that is what the whole definition and the usefulness of potential was all about. So that once we get potential, we can get potential energy by multiplying it by the charge. So looking at this configuration, I would say that the 1 over 4 pi epsilon naught, the charge of number 1, what did they call it? Just Q? Q ball. You don't see it. I'm going to take your word for it. Oh, actually, they well, doesn't matter. They called it a little q. But it says ball 1 and 2 have the same charge, little q. So I would put this as the potential at point number 2 created from number 1. So then I put charge number 2 at there, and this would be my equation for the potential energy that exists between ball number 1 and ball number 2. Okay? So the potential from ball number 1, how much are you going to place there? At the distance A, that's Q. I'll even put a plus 0 if that helps, because when I add up the total energy, I have to take not only the potential energy, but plus the kinetic energy. So how much kinetic energy do we start with? 0. Okay. So I would say that is my starting point. So I'll just put it as Q squared, 4 pi epsilon naught, A. Okay? So there's the potential energy and kinetic, the total energy it starts with. Where does it go? Well, like I said, that's where the physics came real important. You had to realize that it's going to get its maximum speed when they're in a line like this. Let me stay away from the kinetic energy for just a second. How about the potential energy when they're like this? Is it 0? No, right? It'd be 0 if they were infinitely far away. They're not infinitely far away. How far away are they? Yeah, so again, they are 3A apart. And so again, how much potential do I get from ball number 1 way over here at 2? Well, the distance is A, and A. So there's my 3A. And then I'm going to place a charge Q in its present. So there is the potential it has now. So in other words, it had this much potential, and a little bit later it has a little less. That's the change in potential energy. Where did it go? Yeah, into the kinetic energies of the ball, right? How many are moving? It's going to take a little more physics here. All four of them are moving, aren't they? You see that? That's our mechanics here. Remember, we're on a frictionless table. Let me ask you this. If you think of this as one big object, isn't object 1 pushing on object 2? Any external forces here? Now, what do we know about the center of mass? Way back from Physics 121. If you have no external forces, what do we know about the center of mass? Center of mass doesn't move, right? You have to have external forces to make the center of mass. So before I cut the string, where's the center of mass of this configuration? It's right there. And where will be the center of mass at any other time during the motion? So what's going to happen is as this thing is flapping down, it is pulling these up. Right? And so we have gone from something that looks like this to something that now has 1 and 2 going down and 3 and 4 going up. And so this flapping that I showed you earlier, where the ball 1 and 2 fold over, is more like ball 1 and 2 fold over as this one goes up. You know, so it's more like that than it is just like this, right? And again, that's going to take some of your past physics, some of your mechanics to catch that. Because if you miss that, you probably won't put 4 times 1/2 mv squared. The kinetic energy is clearly 1/2 mv squared, but it's each ball has a 1/2 mv squared. And so that multiplication factor of 4 is where the physics comes into play here as we take these 4. And so now I can work out the problem for what is the maximum speed of ball number 3. Okay? So I've got a little bit of arithmetic to do, but this looks like I have an a squared over 4 pi epsilon naught over a. With that term, when I bring this to the other side, it becomes a 1 minus 1/3. I bring this over, and then on this side of the equation, I guess I'd have a 2mv squared. So this is a 2/3. This is a q squared over a 4 pi epsilon a 2mv squared, a 2 cancels off, and so I can finish this with a q squared, a 3 and a 4 make a 12, an m, and then a square root, and I did a lot of algebra there, hopefully I did it right, but there is the equation for the velocity, the maximum velocity of ball number 3. And for that matter, it's also 4, and it's also 1, and it's also 2, based on my symmetry, based on my mechanics of what's going on. And you can see why the author made that one a magenta one there. It was a good thought process one here. Let me try another one. It's number 44. It actually gives me a chance to pass one of these around. Here's what we call a coaxial cable. We're going to start using it a lot, especially now that we're starting to get away from the science and into the engineering in these next 3 chapters. But take a close look at this configuration. You You'll probably recognize the BNC connectors that we've used a little bit in the lab, and we're going to use more so as the semester goes along. But the wire's been cut and stripped. And so a coaxial cable is designed and has a lot of nice properties. I should probably mention at least one of them, since we've kind of touched on one of them. But if I were to draw a picture of this, maybe I'll just start sending these around there. Here's what you have. You have then, say, a center wire. Okay, and this is why it's called coaxial. So you got this thin wire down the middle. Then there's some insulating material before you get to the second wire, which is again a cylinder around the first one, and hence the name coaxial. And so instead of running a light bulb or a battery and you have one wire that comes in and then you've got a little light bulb and you go back and you got just one simple wire, or maybe the wires you're more used to, if you look at your lamp, when you plug it in, you will see a wire that looks like this. It's connected to then a flat piece of metal that you're going to plug in. You got a second wire there. You've got insulating material around the whole thing. But if you look at this twin lead wire, right, you'll see the two wires. You'll see where the electricity goes down and the electricity comes back. You've got two separate wires. When you look at these coaxial cables, you may not recognize that there are two wires there because the first wire is in the center and the second one is wrapped around the outside. So this is my coaxial cable. One wire here, one wire there. Now, why would it be useful to have one of the wires, what we call the shielding wire, wrapped around the signal wire on the inside? What did we learn about the electric field on the inside of a conductor that is created from the outside world? Right? What does that shielding conductor do? It shields it from the electric field. Exactly. And so the neat part of this design is that if outside of this there was a charge or some other device like a cell phone, and this coaxial cable then is the data coming into my computer, all the stuff that is hopefully happening with my cell phone and the rest of the electronics, as it creates an electric field, this shielding one will send negatives over there, stopping or blocking the electric field. Of course, leave the other side positive. So, well, and I guess they got to be kind of perpendicular, so they're going to kind of turn a little bit. And then they'll go back to what they would have looked like if there was just a point, something like that. Okay. But how does this outside charge affect the charges that are in my signal? They don't, right? They're shielded from it, and that's why it's the outside is the shielding conductor on the outside. So look at that. We're going to use it a lot. That's one of many properties they have. This question is related to that geometry. It's a little different. They're not quite getting into shielding and what we'll call inductance and capacitance, and which is another issue about why these are kind of nice. They, as you probably know, you can send data down this geometry much faster than you could a twin lead wire, which is, you know, why your cable data is much faster than your phone line one. So if you have, you know, DSL tends to be a lot slower than your cable modem. And so we'll get into all of those. But here's what this one says. This one says a Geiger tube is a radiation tube that consists of a closed hollow metal cylinder. All right, so that's this. Closed metal hollow cylinder. So this is my Geiger tube. Okay? If I read it right. A Geiger tube is a radiation detector that consists of a closed hollow metal cylinder of inner radius RA and a coaxial cylinder wire of radius RB. Okay? So this, and I probably didn't give myself enough room, is saying this radius is R sub B, and this radius is R sub A. Okay? I'll read it again. A Geiger tube is a radiation detector that consists of a closed hollow metal cylinder of inner radius R sub A and a coaxial cylinder wire of radius R sub B. The charge per unit length is lambda on the inner wire and a minus lambda on the outer wire. So what they're going to say here, and let me get rid of my quick discussion here, since this was the shielding from the outside world. They're going to say, what would happen now if you charge this inner wire to a value of lambda? Okay? And so you've got a charge per length in there. Would that create an electric field? Now, would the shielding one block it? Well, since it's created from the inside, no, what that's going to do, maybe I'll change colors here, but I'll get an electric field that is radially outward. And so what will happen then on this conductor on the outside is we're going to get negatives building up here. And if there is a negative charge on the outer conductor, that's the end of the story. And that's what they're saying here, that you have a negative lambda on the outer one. Okay? And so what I have is a strong electric field inside there. Okay? Well, we probably need to go back a chapter before we can think about, what is the value of that electric field? What does it look like? Now, here's the idea of the Geiger counter. The idea of the Geiger counter is that if there is some radiation, which radiation is usually made out of some charged particles and come racing in here, and there is a little bit of, well, I'll just say there's nothing in there, but usually there's a gas to amplify them. But if there is nothing, what do you think would happen if a positive charge went in this tube? Wouldn't it get pushed out onto here? And then that would affect the charge, and then what would happen is over here, I would have some kind of electronic box that would detect that this charges, what later on we're going to call current, and it's going to go tick. Hey, we have one little piece of radiation. Tick. Hey, we have another piece of radiation. Tick, tick, tick. We have another pieces of radiation. And so every time something that has a charge goes racing through there, this electric field will push it one way or the other. You could also have a negative go in there. And of course, it would then go towards the center wire. But again, as it goes towards the center wire, it would affect the amount of charge that's on here. And again, with some fancy electronics, we can then count that. Okay? And that's the idea behind this Geiger counter. Now, the real problem here is not to talk about Geiger counters or even coaxial cables. Those are all coming up. Those are wonderful applications of it. Your author here just says, could you give me the equation for the voltage difference between the inner conductor and the outer conductor? What is the potential difference? And that's why it shows up in this chapter, even though it's a little too early between too much with cables yet and too much with Geiger counters. Those are coming up here. But we've got to understand potential, and we've got to understand potential differences. And that's what this problem is. What is the equation for the potential difference between these two? All right, well, let me give it a try. We started this whole chapter by saying the potential difference is negative the integral of the electric field, right? And we started it by doing it between two parallel plates. Remember that one? This is just like the parallel plates, except we don't have parallel plates. We have cylinders. But we got to do that first step. If you remember, what did we do for the parallel plate? Isn't the first thing we did, we found the electric field? So let's do that. How do I find the electric field between these two conductors? Well, that'll take us back a chapter. Isn't that Gauss's law? Shall we do Gauss's law again? Shall I do a Gaussian surface? Maybe somewhere in the middle? Drawn in red here. I will draw a Gaussian surface. And so there's my Gaussian surface. Before I can actually do the integral of the electric field, I've got to say, well, what I know from Gauss's law is that the flux through any closed surface is equal to the charge enclosed over epsilon. And we did it like this. We probably have forgotten it. I know I have forgotten it. I don't expect you to memorize it. I expect you to work it out during the test. That's what I expect, right? So what is the electric field here? Well, again, maybe this will help. Here's this pipe that I like to say, this makes a good view of our center conductor. If you were to stand back on the Gaussian surface, so I'm going to stand back on the Gaussian surface. I'm going to look forward at it. I'm going to say move somewhere along the Gaussian surface. Isn't the charge distribution that you see, and it's not just there, but isn't there charges behind me? I've got charges on this conductor, but I've also got charges on that conductor. But either way, as I stand here looking in front and behind and around me, the charges look the same. So the answer is, what is the electric field on the Gaussian surface? It's constant. I can pull it out, right? What direction is the electric field on the Gaussian surface? Again, it's radially outward. We can say it because what if it is not? So I'm going to point my arm radially outward and maybe lift it up a little bit. Well, there's something that is not radially outward. Imagine taking this big cylinder and turning it over 180 degrees. Because it's nice and long, I have the same charge distribution, right? But all of a sudden now I have an electric field pointing down. That can't happen. I can't have the same charge distribution that at one time I looked at it, it said up. I flip it over, same charge distribution gives me an electric field down. Makes no sense. What makes sense is the electric field can only be radially outward. Because if you have a charge like that and you flip it over, then you have the same electric field. Same magnitude, same direction, and you also have the same charge distribution. That makes sense. That's the symmetry argument. So I would say then that this dA is coupled with a cosine of 0 degrees. And the 0 degrees is the fact that, as I've drawn in this picture, the electric field is going to be radially outward. So there's my electric field, radially outward, radially outward, radially outward. Okay? Now, I suppose for completeness, I better talk about the end of the cylinder. But we did a lot of that in the last chapter. What would be the flux through these endpoints here? Yeah, they're 0 because their dA for this one is that way, but the electric field is that way. So I don't even need to include it. So this side of the equation becomes E, and then it's just the area. The area being 2 pi r times L, L being the length of the Gaussian surface, r being the radius of the Gaussian surface. Now on the other side of the equation is saying how much charge is inside that Gaussian surface. Well, the charge inside of that Gaussian surface would be the charge density times its length. And so, as we did last chapter, we were happy to see the L's cancel off. because we would not expect the electric field to be anything related to our mathematical Gaussian surface. That shouldn't even show up there. And so what we had, and we have again, is that the electric field from this cylindrical charge, this line of charge, looks like this equation. And so it decreases as you go radially outward. So you're saying as you move out, 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 you're going to have a weaker and weaker and weaker electric field. Okay? So the strongest electric field is where? Yeah, where R is the smallest. So it would be kind of this, what R sub B there, the smallest radius there. Right? That's where you're going to get a really small electric field. You'll see in a couple of chapters, that'll be our limiting factor. We'll find out that if the electric field gets too strong, then whatever the material is between those, and the one I passed out kind of had that white insulating material between them. If that field gets strong, remember that insulating material is made out of charges, and you'll start tearing the molecules apart there. So in this case, if you put too much charge on that conductor, your field will get so strong near the surface that you'll start ripping apart that insulating material, and it'll have all kinds of problems from there. It'll tear apart and break down and won't work right anymore. So that's kind of our limiting factor. So this coaxial cable is going to have a limited strength to its electric field, and hence a limit to how much voltage you can apply between them. And that's what we're about to discover. So all of this was last chapter. Now I can get to this chapter. This chapter says, give me an equation for the electric potential difference between those two. And so now I have it. I can go minus the integral. And why don't I just start at the inner conductor, R sub B, and go to RA. Okay. According to what I just did here with Gauss's law, that electric field must be 1 over 2 pi epsilon naught lambda over R. I'm going to move radially outward, so the angle between the direction of the electric field and my integral, the direction I'm going to be walking here, as I move out, 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 is 0. And so there is my integral. Okay. Cosine of 0 is just 1, so I won't pay too much attention to that. The lambda and the 2 pi epsilon naught are all constants. I'll leave the negative there for a moment. And now I just have an integral from RB to RA, dr over R. And so there is my integral. So again, not a real hard integral. Like I said, I don't think any of these we really come across are hard integrals. That's not really what the teaching lesson is about. It's more about the physics behind it and setting up the equations here. What's that integral? Yeah, that's a natural log, right? Natural log of R evaluated from RB to RA. So if I put this in, minus epsilon, or minus lambda over 2 pi epsilon naught ln. Then maybe I'll do this in 2 steps in case it's been a while since you've done your logarithms. But that's nice and simplified. What's that one? Yeah, that's RA over RB, right? And for that matter, I can incorporate the negative. Because if you put the negative into a logarithm, you can do that, which now becomes the natural log of the bigger one, or the smaller one over the bigger one, or the bigger one over the smaller one, depending on which way you like to write it. And so you can have the negative out in front. How did your author write it? He said it should be 2 Coulomb's constant lambda natural log of over b. Yeah. so there is our equation for the voltage between. Okay. Yeah. All right. Cosine of 0 came from this dot product. Okay, yeah. So the dot product is the angle between these two vectors. So I'm going to do an integral. And when I do an integral, I got to look at the two vectors. What are the two vectors? First vector is the direction of the electric field. So that's this blue one. So the electric field's going that way. What am I doing my integral? Well, I am integrating along the direction dr, starting from the inner one to the outer one. So I'm going right from the inner one to the outer one. So I'm going that way. So E is that way and dr is that way. So there's no angle or 0 degrees between those two. Oh, and I never put that one on there. And this was number 44. Another magenta one, by the way. So we did a couple of magenta ones here, 3 magenta ones. First charging that Q, then that little square of charge, then the 44. Well, I saved just a hair amount of time, not much. But I need to say something about the next chapter as you guys get into the lab here. So I'll call it quits for this one here and say, all right, just give me 15 minutes to tell you very little about the next chapter, but enough to kind of get us started so that you'll have an easier time and a better time with the lab tomorrow. And so this next chapter, as I said a couple times, you might be happy to hear, there is no new physical principle. We're not going from Gauss's second law or something like that. We've got our first step of physics done here, and that is electric fields, forces, charges. Okay? Now we're going to start using them. We're going to start applying them and using them for different reasons. So, this chapter 26 is titled capacitance. Okay? And it wants, or I want to teach you, what is capacitance? It starts off by saying, well, what is a capacitor? And so what you'll see, and what I'll show you here, a capacitor is simply a device that stores charge. Okay? You measure its size by calling it its capacitance. And so there is our two words, a capacitor and the capacitance. So the capacitance is the measurement of the conductor. Now the symbol we are going to use for a capacitor is going to be a C. The symbol you're going to use to measure the units is a is a farad. And so a lot of those terms are new. That's why I felt like I better make sure I take some 15 minutes here and say, okay, let me get some new terminology out here. Here's how we like to define a capacitor. I'll start with this. This would be a very simple picture of a capacitor. It's almost identical to the one you're going to use tomorrow in lab. What you're going to do then is measure its capacitance. You're going to change parameters like moving it apart. Does that change its capacitance? Moving it closer together. Changing the overlap between how is this plate overlapped with that plate. What if you have more than one capacitor and you start to hook them together, like this one in an old ham radio? Here is the parallel plates and the other parallel plate. So we're going to call this a parallel plate capacitor. Okay? And in this case, we have 10, 20, 30 parallel plate capacitors hooked together. And we can hook them together in two different ways, which we'll talk about in lab here. Here's a smaller one. Okay? Most of our real capacitors look maybe something more like this. They're cylindrical in shape, whether they be big cylinders or smaller cylinders. Or here's a little bigger one. They're essentially this. They are two metal plates. 1, 2. As the name implies, what is a capacitor? A device that stores charge. Here's how it stores the charge. What if I took a bunch of negatives off this plate and put it on that one? Put a piece of paper or some kind of insulating material between them. There's my storage device. Okay? Now we're out of time. I'm going to show you hopefully some good usefulnesses of why we care about capacitors. I think by the time the semester's over, we'll see 4 applications of capacitors. Okay? The first one is just to say it stores charge. What if I were to put a bunch of negatives on here, which came from here? That means that side's positive and that side's negative. What if the lights went out? What could I do with this capacitor? I can take the negatives off of here, run them through the lights, and as the negatives go through the lights back to the positive, wouldn't that be the electricity then that is running the lights? And that's one of the steps you will do in the lab tomorrow. You take a capacitor and you charge it up and you hook it to a light bulb. It's the easiest step in the lab. You don't measure anything. You just hook it to the light bulb and you watch the light go on. And eventually it goes off. And so you are supposed to see one of the neat applications of a capacitor. It's a storage device. It stores charge. If you want to think of it sort of like a storage tank of water, right? We have water here. It's ready for use. Your bathroom probably has a storage tank in it. It sits behind the john up there and you flush the toilet. You've got a bunch of water waiting for what? Waiting for its opportunity to clear the toilet, right? It's just sitting there. It's stored water. That's what this is. It's stored energy. It's stored charge. It's waiting for its time to be useful and to do something with here, okay? And so this is our capacitor. Now the reason these often look like little cylinders is because once you take your 2 metal plates and put an insulator between them, then you just roll them up, and hence you have your capacitor. And you hook one wire to one plate and one wire to the other plate, and now I can come along and touch one wire to one light bulb and this to the other one, this to my cell phone, and voila, there goes my cell phone. It works now, or there goes the light bulb. It works. Okay? Now, question. It is different in this sense, but it's the same. Let me do the same first. It's the same in the sense it's supplying charge that runs your phone. So a capacitor can run your phone in the same way a battery can run your phone. Difference is a battery is getting its charges after a chemical reaction. So the charges are not already separated, positive and negative. It's hard to get a lot of positives and a lot of negatives. As you'll see these light bulbs we use tomorrow, we will run a light, but it'll only operate for about 30 seconds. So if you're willing to run your cell phone for maybe about 30 minutes, these would be great. Truth is, nobody wants to run their cell phone for only 30 minutes, okay? You need a... So one of the holy grails of this area of electrical engineering and material science is, can we make materials that can get more charges on here and hopefully at some point replace batteries altogether? So, forget just making better batteries. How about no batteries? None of these are just recharging it. I mean, you still have to recharge it. But as you'll see, these things are really nice because you plug it in and putting the charge on there happens in a really short amount of time. So the ultra capacitor would be great. We could run our batteries, we could run our cars. They wouldn't be nearly as heavy. They wouldn't be nearly as toxic. They wouldn't be nearly as expensive. Although, no, it depends on what material. Eventually somebody comes up with it. Yeah. But in the sense of running your cell phone, that's the same. Yeah, same charge. All right, well, like I said, just wanted to make sure I got a good physical picture here for you of what's going on. Let's do this. Let's try this parallel plate capacitor. Since you're going to be studying this a lot tomorrow here, let's say, what is the capacitance of this? And so here is our definition. I said it was a storage device, symbol C. Here's how we define it. We define the capacitance as this. How much charge do you get on one plate compared to how much voltage it takes to get it there? In other words, if I start taking negatives off of here and putting it onto there, my parallel plate will look something like this. So I take a bunch of negatives and I move them over to here. Negative, 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 negative. And of course, every one I move leaves this plate positive, positive, positive. So you can see how one plate is negative and one plate is positive. Fair enough? Now, of course, that's going to make an electric field between them. That electric field is going to make a voltage difference between them. And so what we're going to say is the capacitance is we're going to say the capacitance is how much charge do you have to move in order to generate 1 volt here, right? That's what this is saying. And so how much do I move over? Again, we're back to that ratio like gasoline. You go to the gas station and it says $4 a gallon. Okay? Well, what does that mean? That means that you have to pay $4 for every gallon. That doesn't necessarily mean you pay $4. It doesn't necessarily mean you get 1 gallon. If you did get 1 gallon, you'd pay $4. Fair enough? The same thing with the capacitor. A capacitor is going to do this. We're going to have something like, how about 12 microcoulombs per volt? Ooh, what do I mean by that? Well, I mean I have to move what? 12 microcoulombs of charge for this to charge up to 1 volt. Now, I may charge it to more than that. I may charge it to, say, 10 volts. And so if it's 10 volts, I really moved how much charge? Wouldn't that be 120 microcoulomb? But I have to move 12 microcoulombs for every volt. Okay. Now, as I said earlier, this 12 microcoulombs per volt, we are going to give a name. A name of the great scientist working in the field. And so, Michael Faraday, and so we call this a farad. And so this, we would say the capacitance of 12 microfarads. And that's what you're going to be looking at. Tomorrow's lab is to get you acquainted with this shape and this design. You're going to take a little meter. You're going to do some other things too. But you're going to take a little meter, you're going to hook it to one side, the other side, and you're going to read the meter. And the meter's going to say, what is the capacitance? Okay. And so it's going to be listed in farads. How many farads? Okay. Now, the first part of the lab, you end up using these little guys that, believe it or not, got a lot of metal wrapped into them. And so these are probably in this range of microfarads. As you'll see when you hook this one up, this one you'll probably get a reading of like 150 pico. What was a pico again? Yeah, 10 to the negative 12 pico. So you've got a very, very small amount of capacitance. What do you think might affect the capacitance? Do you think it would change its capacitance if I moved it further apart? Yeah. See, anything that kind of changes the geometry is probably going to change this capacitance, right? Because isn't it the capacitance how much charge I have to move across here? And so I should get a different effect. And so that's part of your lab. Your lab is to move these back and forth, okay, and find out, did it change? How about the overlap between them? Isn't the capacitance related to the electric field? Isn't the electric field related to the charges between them and how they overlap? So I would expect the capacitance to kind of change, to kind of vary a little bit. And so like I said, this chapter and tomorrow's lab, and then starting on Thursday and through next week, is the idea of what is a capacitor? Why is it useful? How are we going to use it? We're going to apply some of our electric fields and charges.